Let's forget the word. This meeting is being recorded. So let me just start. I mean, people are late a little bit. So I don't know if you know this anime character. Anybody knows? Yeah, it's Goku from Dragon Ball Z. So unfortunately, it fell off a shelf on its head, and we weren't sure if it has, had a concussion or something like this. So we decided to do an MR for Goku. So we took him to the scanner, and it's pretty sad actually. So yeah, we took him to the scanner. This is Goku in I mean, it fits in an E-coil, so we put him in E-coil. It's a 16-channel E-coil, and you can see it closer, kind of lying over there. And then the problem is that it's probably made out of ABS, which is a form of plastic, and it's pretty rough. And while it has protons, it has an extremely short T2. So in order to be able to image its brain, we had to use a sequence which is called ZTE, a zero echo time sequence. And the idea in that sequence is that you actually turn the gradient on, and then you apply a very short RF, which the RF will have a high bandwidth that will cover the entire volume. And then you switch immediately from transmit to receive, and then you receive on a radio line. And then what you do is you switch the gradients a little bit. You rotate the gradient a little bit and repeat an RF, a short, very short RF, which also excites the entire volume. And then it reads another line very quickly. So that allows you to collect data with extremely short echo time, on the order of maybe 2 to 6, maybe 8 microseconds or something like that, very short. And so we did that, and here are the results. Oh wait, where are my results? So yeah. So here are the slices. Let me share the slices. Poor Goku. Can you see? Yeah. So here are the slices. I'm walking through the slices. So anybody has an idea what is this thing? Okay, so we go through the slices, and yeah, so these are the slices. And I think the problem that we found, you can see here, it's a little bit grainy, so the SNR is not great. But basically, I mean, I don't know if you've seen the show, it's not the sharpest pencil in the bunch, right? And I think the reason for it, it's pretty much doesn't have a brain. So it's just solid plastic. So obviously it wasn't damaged, but also, nothing to think about. Yeah. So that's the issue. Now the abdomen exhibits a little bit. I mean, there's a few holes here, and kind of like lower density in the leg, probably arthritis at some point that was developed over the years, maybe during the pandemic or something. By the way, Shreya, thank you very much for collecting that data.
Sure, no problem.
Yeah. So anybody has an idea what's the thing on the bright thing on the right hand side? I mean, this is the stick that it holds, and you can see the plastic of the stick. It's pretty amazing. But anybody has an idea what is this thing? It's kind of hard to see from slices, right? Like to imagine slices. So what I'm going to do is actually I 3D rendered it. And let me just show you the rendering. Yeah, so this is the 3D rendering. So you can see actually the body of Goku sitting inside, but what's around it? Does anybody now has an idea? What is this?
The coil and the connector of the coil.
Yeah, that's right. Usually the coil is also made out of plastic, and I think it's also ABS. It has a very short echo time, so it's not a problem. But when you use ZTE, you're actually receiving signal from the housing of the coil itself. So you basically here you see the plastic of the coil. And some of the bright stuff, it might be some more softer plastic. Softer plastic will have a slightly longer T2. And in particular, the cable actually that comes out, the coaxial cable has the cover, I guess, of the coaxial cable is made out of very flexible plastic. And that is actually the brightest thing here. And you can kind of see it here. And it's hollow because there's a conductor inside. See that it's hollow? But that's because of the conductor. So yeah, I thought it's pretty amazing. You can actually see the coil and Goku lying in the coil. Yeah. So safe and sound, no harm done, but still stupid. All right. Any questions? So last lecture, last opportunity to ask questions. Next lecture, we're going to ask questions. Now it's your chance. What's going on? Everybody's okay? Surviving the pandemic, surviving the semester? Yeah? Fine. All right. So what were we talking about today? Oh, any announcements?
Just I guess I'll post the project signups right after lecture, so watch out for that. It'll be first come, first serve. So pick your slot. That's it. Yeah.
Okay. And that's going to be 15 plus 5?
I think 12 plus 3. We don't have enough for 15 plus 5, unfortunately.
So 10 plus 5.
10 plus 5?
Yeah.
Okay.
Yeah, we need a discussion. So
Okay.
aim for 10 minutes plus 5. Okay. And it's going to be recorded and posted on the web. So, you know what I mean? You know what it means, right? It's out there. Okay. Where were we? What topic?
Parallel imaging.
Oh, thank you. Thank you. Thank you, Amy. Yes, parallel imaging. That's right. We're talking about parallel imaging. Actually, one of the most exciting topics we'll be talking this, this semester. It's a really cool approach that actually uses, a combination of, hardware, electromagnetics, as well as signal processing, linear algebra, and so on and so forth to perform MRI reconstruction that are not just Fourier involved. So far we only dealt with, Fourier-based methods. Now it's not a Fourier-based method. It relies on the Coil sensitivities in order to perform the image reconstruction and figuring out where stuff is located. Okay, and as it unfolds. Okay, so the screen is being shared. Okay, so we talked about the basic idea of parallel imaging and its premise, the fact that we are for every phasing code, or for every measurements that we make in an MR, because we digitize all the signal coming from each one of those channels, we have a lot of measurements coming out. It's not a single Fourier measurement. It's a Fourier measurement that's coming from different coils, and each one of them illuminates the sample in a different way. And so that option gives you the possibility of maybe using those coil sensitivities as part of the reconstruction in order to reconstruct the unweighted image, okay? With perhaps fewer number of Fourier encodes. So the basic idea is to, multiple coils give you more SNR, so you trade the SNR for speed in a multi-coil acquisition. And the way to do it is we're not going to skip out readout points. Like along the readout direction, it doesn't make sense to remove measurements because we already collect them. And so we could either store them and use them. I mean, there's no point of discarding them and then reconstructing them, right? So it's not going to be along the readout. The readout is pretty much continuous, and it doesn't save us time to remove measurements from there. However, it does make sense to remove measurements, for example, from phasing codes. So if we skip phasing codes, well, that is definitely a save in time. Okay? Now, skipping phasing codes leads to aliasing. So here's an example of a brain image. This is it's a very special brain. Let's call it Professor L. Anybody has a idea who's that brain belongs to? Beautiful brain, right? Anybody?
Must be Chu Lei Lu.
No, but a good guess. Let's see. Okay, so let's do that. Okay. Anybody else? Give me a letter.
T.
T?
T.
Another letter.
A.
Another letter. Come on. We don't have a lot of time. Give me a letter.
You.
I.
Yeah. What?
I,
R,
M.
Larson.
Aha, good job. Yeah, Larson. Yeah, that's Peter Larson's brain. And you can see the fat that he has here, kind of on the edge, kind of like a little bit chubby on the back, you know. Yeah, he's a professor at UCSF. Does a lot of UTE, ultra short echo time imaging, as well as lung imaging, as well as carbon-13. Anyhow, so here's the idea. If you image, this is the sensitivity of the coil from this direction. This is the sensitivity from the coil. And I'm only showing, by the way, the magnitude sensitivity, not the phase, right? Like there is also phase associated with the sensitivities. And now when you skip phasing codes, then the image that you get from the left coil will give you this aliased image. The image that you get from the right coil will give you this aliased image. Okay. Yes, makes sense. Okay, so it's two different alias image. And this is with R acceleration. R, it's usually called acceleration. I don't know where the R comes from, but that's from Prusman's paper. R factor of 2, basically we save twofold scan time by aliasing this way. And now we need to come up with a way to combine those images into an image that looks like that. Okay, and the question is there a good way of doing that? Okay. So here's pretty much the deal. Okay, hold on. Let me use some reference here so I can write some stuff for you. Yeah, so here's the deal. We have two receiver coils, okay? Two receiver coils, so two images, right? And then basically two source pixels, this source pixel and this source pixel will alias into one image, right? So into one image pixel, okay? So these, again, two source pixels, these would alias to this pixel in this coil, and then these would alias to this pixel. Only for this coil, this one will be weighted by R2, right? By this position. Okay, so we've got this. These two coils are combined to these two pixels are combined, and we get an aliased version here in this pixel. And then we also have a situation where for for the image, the second image, these are also combined, except that the combination is different, right? Because we got in one case, sorry, I actually didn't put R2 here, but yeah, this is R2, and this is R1. So let me just go back. Yeah, so this R2 is multiplied by this sensitivity, and then this R1 is multiplied by this sensitivity. Sorry, again, mistake. It will take me time, but I'll iterate and converge into the right solution, right? So for coil 1 is a result of sensitivity 1. Okay, so image 1 is the result of sensitivity 1. And what happens there? Well, the sensitivity in position R1 is multiplying by the image value in R1, okay? And then this is added to a situation where you have the sensitivity at position R2 times the coil pixel R2. These two are added together to give you the target pixel RP. Okay, so this multiplied by that, this multiplied by that, they add it together, and then you get this. Okay, so actually we can write this down. We can write it as the image at R1, right, is multiplied by S1 at R1, and then added to S1 at R2 multiplied by the image at R2, right? And that gives, oh, come on. Anyway, I'll do it. I'll do it one more time, and I'll do it in a nice way. So the image at R1 is multiplied by S1 at R1, and then added to the image at R2 multiplied by S1 at R2, and that gives me M1 at RP. Okay, so this is the value of this pixel is a result of a summation of two weighted values. Okay. Now, anybody wants to say what is the equation for this thing? I'm going to write it down, but based on what you're saying. I'll start. Okay. The image at R1 multiplied by S2 at R1, the sensitivity now here, plus what? What other pixel it's being combined with?
It'll just be the same expression, but at R2.
Almost. So it's M at R2 multiplied by the sensitivity. Which sensitivity?
S2.
Oh, S2 at R2. And that equals to M2 at RP. Okay, which is this pixel. So I got two things that I know. I know S1 at R2, I know at S1 at R1, I know at S2 at R2, I know at S2 at R1. We said we know the sensitivities, but we don't know M at R1 and M at R2. And we don't know, yeah, that's what we don't know. So these we don't know, but these are just two values, right? So I have two values, two unknowns, and I've got two equations. And these are linear equations, right? Yes. This is M and this is M at R1, or the same thing. That's the same thing appears here, the same thing. So I have two unknowns. Folks, yes, nod, like just give me an indication, right? Okay, two unknowns to equation, okay, well, we can do something about it, right? First of all, I can write it in a nicer way, right? I can actually write it this way, right? Like this is the unknowns, M at R1 and M at R2. And then M at R1 is multiplied by S1 R1, and then M at R2, S1 R2, right? And that gives me M1 at RP. And then the same thing at S2 R1, S2 R1. Basically, this is what I'm writing it, right? And then there's noise. And I can write pretty much MS at RP equals S times M plus N, right? Where this is a vector of whatever aliases, right? Like these values. Okay. So this is the forward equation, right? So two measurements of MR1 and MR2, each with different weighting. And the weighting is really a coil sensitivity matrix, right? This is a coil sensitivity matrix because it has S1 at position R1 and S1 at position R2, and then S2 at position R1 and S2 at position R2, right? So in this direction, it will be the coil. And in this direction, it will be positions. that alias. Okay. So that's easy. There's a solution for this. What is the solution for this? Minimum variance solution, right? Like I mean, very similar to what we did in the case where we didn't actually undersample. Like when we had all the data and we wanted to combine all the data there, this matrix was different. It was n by 1. Now it's n by 2. Okay. 2 because only 2 pixels alias on top of each other. Because before it was 1 in the position direction because there is no aliasing. Now there is 1 alias because we only undersample by a factor of 2. So it's n by 1. N meaning the number of coils. Okay. All right, so there's a minimum variance position. It's basically the same thing. This is exactly the same equation that we used before. So the solution is pretty much S conjugate. This is the covariance matrix inverse S minus 1, S conjugate covariance inverse minus 1 times MS at RP. And the only difference is that the size of the matrices are now different. This thing is a 2 by 1, right? Because we got pixel from coil 1 and pixel from coil 2 at the same position. The result will be 2 different pixels, M at position R1 and M is position R2. That's here. So it's a 2 by 1. And then this is a 2 by 2 and this is a 2 by 2. Before, that was a 2 by 2 and that was a 2 by 1 and that 1 by 2 and this was a 2 by 2 by 1 before, right? Something like that. Does that make sense? Okay, so 2 aliased reconstructions unfold into 2 image pixels. So effectively, you got 2 pixels that are aliasing, one in coil 1 and one in coil 2. We unfold them and find the value of the original image at position 1 and position 2. Does that make sense? Super simple, right? In the general case, we'll have something like that. Let's say we accelerate, we undersample uniformly by a factor of m. If we undersample uniformly by a factor of m, I will get m pixels overlapping on top of 1 into one place. Okay, before I was 2, 2 pixels were overlapping. If I remove a lot of lines, such that I'm undersampling by a factor of, let's say, 8, I'll have 8 overlaps. Okay, all right. So R equals M. The number of coils could be, I don't know, could be N, right? Like it could be something else. You know, I could undersample by a factor of 2 with 4 coils. I can undersample by a factor of 3 with 8 coils. You know, there's all these combinations, right? So in that case, you know, M, which are pretty much the folded pixels, will be M by 1, right? Because there's M folding into a particular no, okay, hold on. These are the folded pixels. Sorry, these are the folded pixels. There's a n by 1 folded pixels. Why? Because there's n coils. Okay. What are we going to reconstruct? Well, we're going to reconstruct m pixels because each, you know, m are folding on top of each other. So we're reconstructing m. So S would be an n by m, and the noise, of course, will be n by 1, right? So you can do the math yourself if you're not, you know, NM, you know, that kind of stuff. So you could look at yourself. The solution is exactly the same. Okay, the solution is exactly the same, as long as this thing is determined. Like what happened if I would have 2 coils, but 4 times undersampling? Well, that will be then degenerate, that will be underdetermined and will not be able to perform the inversion, okay? Now, there could be a situation even when, let's say we have 8 coils and 8 foldings, but that also may be underdetermined or ill-conditioned, right? That could also be the case. It depends on how the pixels are folded and what are the coil sensitivities. And that needs to be managed. Okay. So what I'm going to do now is effectively what's happening is that we take these two alias pixels, one pixel here and one pixel here, and then we perform a linear combination of these, a weighted linear combination based on this reconstruction matrix to get this value of the pixel here. And then we take those two pixels, the alias one, and we do a different linear combination to get this value. And then we do that for every single one. Okay. Now, basically, the problem of reconstruction becomes separable for every, in this case, every 2 pixels. We solve 2 pixels at a time, and we shift, and we solve 2 pixels at a time. And here is just a single pixel at a time. So, there's going to be a different matrix for this RP, and there's going to be a different matrix for this location, and there's going to be a different matrix for this location. Okay. And so basically, I'm going to have a bunch of these small matrices that I need to invert, and then I'm going to solve and recover 2 pixels at a time here, right? And put them in the right place. And that's a very simple reconstruction, right? Like it could be efficient, very parallel, very nice, right? And the reason that it's so separable is because when you undersample K-space in a uniform way, then you've got this really pure aliasing that happens. That is actually not true if you have a variable density undersampling or if you have radial. Then you've got every pixel is overlapping with every pixel. And now you cannot solve for each one separately. You'll have to solve a really large problem. And that is often solved iteratively. Okay, like in an iterative fashion, because it's just not possible to perform these inversions. But for the simple case, where you undersample uniformly, factor of 2, factor of 3, then it's really just solving, an inversions of 3 by 3 matrices, 2 by 2 matrices, very small, but many, many times. Okay, pretty cool, right? All right. So here's the issue. Okay, let's kind of look at what's going on here. So let's look at a hypothetical.
Yeah.
Thank you.
Oh,
Thank
I'm
you.
also bad. Sorry.
Çok güzel. So let's look at the hypothetical situation where I'll just pick numbers here. Although the numbers should have been complex valued, but I just picked some values, right? So here's a situation where the coil sensitivity at R2 is 0.8 and at R1 is 0.1. For the second coil, it's 0.15 at this position and 0.85 at this position. Okay. All right. Okay. So the equations that I have when I do twofold undersampling is M at R1 and M R2 multiplied by this matrix equals to that. Okay. Now, okay. So now I want to perform the reconstruction. So I'm going to invert this matrix and multiply by this. Right? Invert this, multiply by this, and I'm going to get that. Okay. So this is the inverse of the matrix. The inverse of the matrix is 1.28 and minus 0.15, minus 0.23, and 1.2 of those pixels. See, M1 at RP and M2 at RP. And so in order to get M, the original pixel at R1, I will need to take M1 and RP and multiply by 1.28, M2 at RP multiplied by 0.15, and then add them together to get the value of the unfolded pixel at R1. Okay. Now, the thing is that measurement that I have M1 at RP, it's noisy. And that measurement at M2 at RP is also noisy. And that is actually, let's assume that those are independent, right? We said that we're not, but let's say this is a pre-whitened result, like it's independent. Okay. So this has noise with some sigma sub n, you know? Okay, some sigma. All right. So what is then the standard deviation of the value, the estimate of the value at position MR1? Well, I mean, it's 128 times sigma 8 minus 15 times that, right? So variances add, if you remember. So this is the variance, and this is the variance, right? And effectively, what I'm going to get is this. Okay. So I'm going to get 1.29, like the standard deviation is going to be 1.29 sigma n. And then for the second case is going to be 1.22 sigma n. Just by, you know, by calculating what would be in the standard deviation. Okay. So now I know actually what is the noise standard deviation of the output. Now the question is it good? Is it not? Like how do I compare that to what situation I would have compared this to? Well, I would like to compare that situation to the one that I did not undersample, collected all the things, and I don't have aliasing, and now I'm going to do optimal combination. Okay, to the situation where there's no aliasing. Let's see, in that case, what will be then the standard deviation? So in that case, if there's no undersampling, then my equation is the following, is 0.8 times MR1 will give me M1 R1, and 0.15 times MR1 will give me M2 of R2, right? So for pixel MR1, you know, it's just a 2x1 now. And now the reconstruction, this is the reconstruction matrix from MR1. It's 1.21 and 0.23 times that. So now I can also compute the noise standard deviation that I get. And the noise standard deviation that I get is 1.23 sigma. Okay. So something changed. The fact that I undersampled and I used actually this matrix in order to perform the reconstruction, and that matrix actually, if you look at its eigenvalues, they're not uniform. There is some ill-conditionedness, like the measurements are not orthogonal. Like actually, if you look at this, it's not orthogonal. This is not an orthogonal matrix. Non-orthogonal matrices will increase the noise, will amplify the noise because it's not orthogonal if I try to invert it. And the cost is compared to the case where I don't use this matrix in order to invert it, right? Like I just use the combination, the perfect combination. So there is a cost associated with it. And that cost associated with it is called the G factor or the geometric factor, because it depends on the geometry of the coils and their coil sensitivities and how I'm undersampling. And in this case, it's 1.05. So effectively, I've got a noise amplification of 5%. Just because I'm using non-orthogonal coils. So this is just due to the reconstruction. It has nothing to do with the fact that I undersampled by a factor of 2. That I lost square root of 2 of SNR already. Now, in addition to that square root of 2 SNR loss, I'm also losing 5%. Does that make sense? And this is the way to calculate G factor, is compare basically the situation where you're undersampling and to the situation where you're not. And I can do the same thing for M at R2. I didn't calculate for M at R2, but I just calculated for M at R1. Okay. So you could also see that the noise amplification, that G factor, is actually dependent on the position. It depends right now on R1. Like, and it might be actually different for R2. So there is actually a non-uniform amplification of noise because I'm using different matrices to compute the solution for different positions. Okay. So in general, you can actually calculate what is the G factor by looking at the noise covariance matrix and the sensitivity maps. And this is taken from the paper. Basically, you compute SH, which is S transpose conjugate. This is the covariance matrix inverse 1S, and all that's minus 1. And then you look at position row, like that is I guess that pixel that you're looking for, and then multiply by this at position row. So if I'm looking at, let's say, the second pixel within the one that I'm trying to unfold, then row would be 2. Okay. And so it really depends on where it is. You can get a particular G factor. Now the acceleration R, depending on the number of phasing code in the full case, divided by the number of k-space points or the number of phasing codes in the undersampled case. So if I collected half of my samples, let's say the full case based on Nyquist would be 256, but I collected only 128, then R would be 2. Okay. So the SNR, in the reduction case, in the case where we are undersampling of a certain pixel, will be the SNR of that pixel in the full case divided by square root of the acceleration. That kind of makes sense because that's this, I reduce my number of I reduce my measurements by a factor of R. So I lose square root of that, but then also times this geometric factor of that particular pixel. Okay. And it really depends on, the situation, like in what, where are my coils and how I'm undersampling such that things are going to be done. So here's the case where this is, this is from the paper. And this is basically image from one coil, just showing like an image from one coil. This is the full image, and that's an image from one coil. And then this is another image, and that's with 2 times undersampling. And you see that in one coil, you got this folding, right? And this is 2.4 undersampling, and this is 3-fold, and this is 4-fold undersampling. On the right-hand side, you see what's called a G factor map, or this G here, this G that depends on position. And you see that that G starts increasing as you move and you speed up more. Like then the ill condition is starting to appear. At 4 times acceleration, with I think 4 coils, you'll get G to be more than a factor of 10. More than a factor of 10 means that you amplify your signal by a factor of 10. In order to buy back that SNR, you'll need to average 100 times. Basically, it's useless, right? So any G factor, above 2 is really pretty much a no-go. Okay, unless your SNR is like super high. Does that make sense? Any questions? Okay, so here are some practical aspects. Parallel imaging works in the phasing code directions. Okay, in the readout direction, remember the field of view comes for free, so we don't care about that. Like it's because we collect all the samples at we're only depending on your ADC time, so you really don't care about it. So what you really need is you need the coil sensitivity variation to be in the phasing code dimension. That is the only, the change in sensitivity along the phasing code, that's the most important part, okay? And so the acceleration, the amount of acceleration cannot exceed the effective number of coils. And what do I mean by effective number of coils is, you might have 4 coils, but they might not vary in the same degrees of freedom, like 4 orthogonal functions along the phasing codirection. Maybe there'll be just kind of 2 principal components that you can actually represent along that dimension. And so really, you cannot accelerate more than, let's say, a factor of 2. So anytime that you try to accelerate beyond what the coils allow you, that will lead to more unknowns in equations or to a very ill-conditioned situation or underdetermined situation. Does that make sense? Okay, so here's actually an example. This is also a brain, and this one is hold on. Yeah. Okay, pick a letter.
A.
A? Quick, come on.
C.
E.
I'm going to start 1, 2, 3, 5, and then I'm going to put like a line. So you're going to lose, right? Anyway, 1. What did we say?
U.
J. L. I.
Thank you. Julie. Yeah, this is Julie DiCarlo. She actually now at UT Austin, but she used to be at Stanford, and I scanned her during my PhD. She was a graduate student. Anyway, now she actually works for John Tamir, who was our visitor last time, which is funny. World, comes around, turns around. Okay, so here's a situation where we have a coil, 2 coils in this orientation, and we have 2 coils in this orientation. These are the sensitivity maps, right, for these coils. And these are the aliased images because we undersample in the phasing. So the readout is from left to right, and the phasing code is top down. So we basically not collect the one with the lines. And the question is, for which situation the reconstruction is possible? Who wants to go?
A should be possible, but
Okay, let's see.
only one.
A should be possible. Why?
Because the sensitivity maps give you like different weightings for the
But-
different alias points.
Okay, so the sensitivity maps vary in which direction mostly?
Oh, the up-down direction.
Up, down, right? And we undersample in the phasical direction, which is up, down. And so you can see that those 2 images look very different in the up, down direction, right? So yeah, that gives us the ability, oh yeah, we could probably reconstruct it. But in this case, look, I mean, it's, well, there is variation in this, but it's the, like this is just multiplied by some value, but it's kind of the same as here one. It's just, it's just darker, but it's the aliasing looks exactly the same. You know what I mean? So because we undersample in this direction, then the fact that the coil sensitivities don't vary much here it mostly varied left to right, then I'm going to have a hard time. This is going to be way more ill-conditioned than this case. Okay, so we can possibly recover it by a factor of 2 and from A, but not from B. Okay. Okay, so now I have 4 coils. Coil here, coil here, coil here, and coil here. This is the readout direction. And I'm saying with 4 coils shown and an axial image, this is an axial image, the readout is AP, anterior posterior. What acceleration would you expect to be able to do? Okay, no acceleration, 2, 3, 4, and 5. We have 4 coils and we have a readout here. Phasing code is in this direction. Okay, so what is the acceleration that you expect to do?
Two times.
Okay, why?
There's 2 effective coils along the phasing code direction.
Okay, so this is the phasing code direction. This is the phasing code direction, right? And if you think about this, in this direction, these 2 coils kind of do the same thing. As I move there, you know, they don't change. I mean, they change in the same way, right? And these 2 coils, you know, they also vary in this direction. But, and then these 2 coils mostly vary in this direction, right? As opposed to like it combined. So yeah, you're right in that sense that while I have 4 coils, really there's kind of, I can kind of combine these 2 together and combine these 2 together and say, you know what, yeah, they vary, but really this doesn't vary as much as this one, right? In along this direction. So I got 2 effective coils approximately. Okay. Of course, you need to kind of really analyze it, but technicians actually, that's what they do. I mean, they need to know how to accelerate. So they need to kind of like calculate that in their heads based on the coil element placing. And so, yes, the answer is 2, because these pretty much provide similar sensitivity in this direction, and these provide similar sensitivity in the other direction. Okay. All right.
Can I ask a question?
Yeah.
Technicians don't really think about reconstruction, or do they? Like, why does a technician need to think about parallel acceleration factor?
Because they're going to prescribe that. They're going to say, you know, they're going to prescribe a scan now, and they're going to prescribe the amount of acceleration that they want to use, and they need to prescribe the right direction of acceleration. And they are also the ones that are placing the coil. So they really need to know in which direction it varies. Otherwise, the image they're going to get is going to be crap. So they really know what coils to put and, you know, what acceleration they could potentially do. I mean, there's guidelines from, you know, from the manual and stuff like that, but I mean, they really need to know that. So, okay, so here's another case. 4 coils, same 4 coils, an axial image, but now this is out of 3D. This is a 3D acquisition. So we collect pretty much, you know, 3D, like 2D, 2 dimensions are phasing code, 1 dimension is a readout. And the readout is into the page. So there is a 2-dimensional space of phasing codes. Okay, does that make sense? So effectively, I can kind of sample, I can think of sampling now as points because the other direction is fully sampled. And so now I can undersample in 2 directions. I can undersample both in, you know, this, or I can undersample in this. And the question is, what acceleration would you expect in this case? dang, 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 dun, 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 dun. Yeah, Anita, you want to say something? Save the day.
Thinking 4 because you have sort of like 4 independent coils in this case, because you're fully sampled in the other direction.
You said, you know, if you have 4 coils and you can undersample in 2 dimension, potentially maybe you can undersample like 4, but you said an important word. You said you have 4 independent coils. And the question is, are they really completely independent, you know, from their sensitivity point of view? Are they completely orthogonal in terms of their sensitivity functions?
Almost, or it depends, or something.
So the answer really is 3, approximately. Because if you go to 4, you're pushing it. You're pushing it too much because now you're going to be very ill conditioned. You're going to use 4 equations, 4 unknowns, and they're not orthogonal functions. So your geometric factor is going to be very high. If you're doing 3, maybe it's not going to be as bad. So yes, you can do more than 2, less than 4, probably 3, maybe 2.5.
What does it look like when you do 4? Does it just come out all blurry or something?
Yeah, we'll get to that in a second. Okay, so parallel imaging reduces SNR because of reduced scan time. You use square root of scan time. It further amplifies noise because coil sensitivities are not orthogonal, and that refers to as the geometric factor or geometry factor or G factor that is spatially varying. And it's a function of both the coil sensitivity and the acquisition geometry. Because I could, for example, do a phasing code in the SI direction, superior, inferior, or left, right, or anterior, posterior, or it depends, right? So that is going to affect my, my geometric factor. And this applies to all the type of methods, SANS, GRAPPA, or whatever you're going to be using. This is an inherent thing that you're going to rely on, you know, coil or functions that are not orthogonal, in addition to phasing, like Fourier encoding, in order to invert the equations. So here is the result of parallel imaging and noise. This is, these are, I don't know, some fruit. And this is a fully sampled acquisition, and we accelerate in the left-right directions, okay? So the acceleration is in this direction. We undersample phasing codes in this direction. This is an image that is 1.9x accelerated and looks pretty good. This one is 2.9 accelerated. Now what happens? Well, now you start seeing the effect of the G factor. You start seeing more noise. First of all, the entire image is noisier, right? Because we lost square root of 3 or 2.9 SNR for sure. In addition to that, there are regions in the image, in particular here in the middle, where you see more noise than other places. And that's because in, you know, unfolding those pixels is harder. It's more ill-conditioned. You know, they don't have a lot of variation in the sensitivity of these 2 alias pixels that are aliasing on top of each other. And if I push it to 3.8 acceleration with the number of coils that are used here, you can kind of see really bad noise amplification that is going on, right? Because of I accelerated too much. And that's, Anita, is how it looks like. Okay, you see it's just areas, some areas that would be significantly amplified by noise, because for those, solving the equations there is really ill-conditioned.
So there's coils around it in this direction, right?
Well, I don't know exactly how the coils are, but probably there were coils or something like that. Probably 8 coils, I think. And you
Well,
accelerate in
just
one
that
direction.
The phase was that way, but the noise went that way, which is, did you expect the noise to go that way?
Yeah, because I try to combine, you know, 2 pixels, like one here and one here, to result in this, right? So, you know, because you accelerate only in this direction, so the coil sensitivities vary such that, you know, these areas are very ill conditioned. So it really depends on the sensitivity of the coils.
What
It's
about
not that the noise is not spreading. It's a result that, you know, solving for this pixel is ill conditioned. And because of the coil sensitivities, you know, how they fold on top of each other and how they are orthogonal, you know, then you get results that looks like that.
And then these numbers of acceleration, 1.9 or 2.9 or 3.8, would the technician have prescribed, oh, I want an acceleration of 3.8, or
Yeah.
you just, that's a field on the GUI?
Yep. Okay. So the geometric describes the noise amplification due to the unfolding. Low is usually good, and high is usually red and is usually bad. This is kind of an example where you're seeing, like in papers, when you read papers, they go like, oh, we made this array. This is 2-fold acceleration, really good G factor, like no problem. When you accelerate by a factor of 3, you can get up to about, you know, 1.9 at a peak G factor. It's a peak G factor, right? Because some other places is not. And then accelerating a 4 in 1 dimension will give you, you know, really bad G factor. You know, factor of 4 is pretty bad. Now, sometimes you would display 1 over G. And the reason for it is because G factor will go from 1 to infinity. But this dynamic range is not very nice to display. So if you present 1 over G, then you present the retained SNR as opposed to SNR amplification. Noise amplification. Instead, you do retained SNR. And so 1 is good. And so in that case, low, blue is bad, and then red, which is, you know, as close as possible to 1, is good, right? So you'll see maps like that, and that says, you know what, in most places, I'm retaining 100% of my SNR, except to some places. And here, this is really bad. I'm actually retaining about 10% of my SNR because of the G factor. I like this better than that, to be honest, because this really shows nicely what is left, you know? Because you would think R4, you know, like G factor of 4, not bad, but like it's really 25% SNR now. You know, it's like, you know, that's pretty bad, right? But 4 times, you know, who cares? But you know, I don't know. It's the same number. But... Okay, so here's the really interesting thing. So on the top, it shows what happens when you accelerate and how SNR is reduced, right? So this is the full image, and this is a factor of 2, and this is a factor of 3, and this is a factor of 4, right? And as you start going, you start seeing, you know, significant amount of noise that is being generated, right? Like being amplified and showing up. This is the result of both collecting less data and the G factor. Now, in this experiment, they did averaging. So they accelerated by a factor of 2, but they collected 2 images and then averaged them. Here, they accelerated by a factor of 3, they collected 3 images and averaged them. So here, you don't lose SNR because of scan time. You lose just SNR because of acceleration. And you can kind of see what the result of acceleration, you know, gives you, you know, really bad SNR, even though you didn't sped up, you know, acquisition time. Like you see the different SNR between these is pretty bad, right? So that's no acceleration, but the fact that you're using the coils in order to do the reconstruction, you know, gives you a hit. And it's really a nice image, you know, to show. But the combination of the acceleration and the loss of SNR could be detrimental. And this is really non-diagnostic. This is non-diagnostic. This is somewhat diagnostic, you know? So that's what you have to be aware of when you speed up. Okay, so this is the case for 2D acceleration compares to 1-dimensional acceleration. So this is a 3D acquisition with an 8-channel phased array that is oriented this way. The readout is in the SI, so head to foot direction. Okay, so it's like inside. That's the readout, it's inside. And so now you can undersample in 2 dimensions. And what you could do is you could accelerate just in one or in both. Okay, and so this is the fully sampled case. This is twofold undersampling in the up down and the left right, and that is the reconstruction. But if you just want to, this is the same scan time of the 2 acquisition, but here I accelerated only in one direction by 4 times. Here I accelerated 2 here and 2 here, resulting in 4. Here I accelerated phasing code only in this direction. And you can kind of see, first of all, how there is residual aliasing that's left, because it's, and then how much SNR, like noise amplification, much more noise amplification. So because the coils are situated this way, they're in 2D, you really want to undersample in 2D as opposed to in one direction. Because when you undersample in one direction, pretty much you almost have 2 coils or 3 coils. That's one direction. But if you accelerate in 2, you have way more. You have maybe 4 or 5 effective channels. Okay. All right. So here's a question. For a 3D scan, select the appropriate readout and slice selection direction for this anterior posterior array. This array has 4 by 4 elements, and on the back has 4 by 4 elements. Okay. What is the best choice for readout and slice selection for this case? Not a trivial answer. So there's a lot of things to consider here. You want to consider acceleration, but you also want to consider field of view. And remember that the readout direction, the field of view is actually comes for free.
I think it should be C.
B.
What? Who said B?
B.
What about D? You know what AP is? Anterior posterior, right? From an acceleration point of view, D would be perfect, because you would read anterior posterior. So now you'll have effectively 16 channels that vary along the phasing code direction. Right? So there we could, right? It's like you have basically 4 by 4 in the direction that you are undersampling, right? Like if my arrow would go, this way, right? Like through the body, that would be the readout. Then in these 2 dimensions, here and here, I would have the phasing codes, and then I could, I have 16 effective channels in that direction, right? In these 2 directions, effective. Does that make sense? Because it's a 4 by 4, and this is the phasing code plane. But the thing is that these are very large dimensions, and the body is usually actually, the abdomen is much flatter than how long it is and how wide it is. So the readout would be in the shortest direction, which is not efficient. Because you want to actually use the readout in a large direction, because the field of view comes for free. So what you really want is to have something like reading in this direction. So readout should be in this direction. And when you read out in this direction, where do the coil varies in the phasing codes? Like where's the phase and where's the slice? You know? So phasing code would be, for example, or in this direction, and then the slicing code would be AP, for example, right? And that is actually or sort of left right, I guess, or something. Read SI, slice, LR. So yeah, read out in this. And then slice. Oh, yeah. You want the slice to be in this direction because of the hands. Because you could remove the hands by doing slice selective. Does that make sense? And then the phasing code should be in the third direction. So effectively, from that point of view, you have, kind of 4 by 2, 4 by 2 acceleration. Like you have a 2 in the AP direction because, these 4 and these 4 are kind of the same. So in the AP direction, you'll get 2 coils. And then in the left-right direction, you have 4 coils, right? Because you have 1, 2, 3, 4 coils in the left-right. Does that make sense? So it's not trivial. Like you think about a technician now, needs to think about that. It's like, like you need to know a little bit, do some accounting, do some signal processing, under determinus. But the hands are a problem. That's why you want to do slice selection in this direction. Okay, for a pediatric 3D acquisition, select the appropriate readout and slice selection direction for this anterior posterior coil. There's a reason, yeah. What do you think? Let me argue, and because we're running out of time, let me argue it's actually complicated. And the reason it's complicated is really depends on the size of the child and the anatomy that you're actually looking at. Okay, because you could have this 32 channel coil. So this is 16 anterior and 16 posterior, okay? But if you actually look at, the size of a child versus age, you see that, size or their length increases versus age. And if you actually look at the effective number of arrays that are actually seeing the child, so here, for really small kids, you would have maybe 2 channels. For more, you have like 3 channels. For as the child grows inside, you have more channels that you can actually use because the body is bigger. So for a small child like this one, well, yeah, you've got 16 channels, but really 1, 2, 3, 4, 1, 2, 3, 1, 2, 3. These are just 6 coils out of the 16. That are effectively seeing the child. These coils over here, these coils over here, sees empty. You're really not using them. So now you think of it, well, yeah, my field of view is small, so that allows me to maybe collect less data, but based on that field of view, I can only accelerate 2 in this direction and I can only accelerate maybe 3 in this direction. But if you, or less actually. So if there was an adult, you could accelerate more. Does that make sense? So really the size of coils needs to be adjusted to the anatomy, and that is a critical thing to do. And just to show you, this is again, one of my favorite paper from MGH where they actually did that. They adjusted the size of the coil to the different size patient. And then when they do that, this is a neonate coil, this is a 7-year-old coil, they're all 32 channels. So the channels here are smaller and more condensed than this one. And this is kind of the result that I showed you in the talk that I gave about flexible coils. It's pretty much if you take a small head and put it in the 4-year-old coil, you'll see that you get very nice SNR. But if you take the same small head and put it in an adult coil, you'll have significantly less SNR. And now if you actually look at a G factor map with 3x3 acceleration, this is 3x3 acceleration, you know, for an infant, you know, the retained SNR is pretty good. It's almost 1. But if you try to accelerate an infant image in an adult coil, crap. Return SNR would be less than 1%, 10%. Does that make sense? Because not all the coils are seeing the patient in the same way. $457. Let me just talk a little bit about coil sensitivities, okay? And then I'm going to finish, and then I'm going to say goodbye, and you know, the end of the class and stuff like that, and then next week we're going to do the projects, right? So here's the classic way of doing things. You obtain a body coil image, and then you obtain coil images, okay, that are not undersampled. They could be maybe, yeah, they're not undersampled. So you collect an image using the body coil, which is uniform, but low SNR. And then you collect coil images. You collect, you know, you acquire basically 2 full images, 2 scans. This is 1 scan, and this is 1 scan. In the first scan, you get a body coil that's uniform. And then in the second scan, you get all the individual coil images. You take the surface coil images and you divide them with a body image. And so what is left then is a noisy coil sensitivity map like that. Okay. And then what you do is you try to remove a lot of that noise by saying, you know what, this has to be smooth. So let's fit a, you know, a polynomial, like a high order polynomial to this smooth function. And now we've got ourselves our coil sensitivity. Okay. Now, the cost of that is, yes, I'm going to accelerate the next image, but in order to accelerate the next image, I can now collected 2 images just to estimate what the coil sensitivity is. Okay. Now, the other option is, you know, not to obtain a coil image and say, you know what, I'm just going to compute the square root sum of square of the individual coil images in order to kind of estimate a uniform. And if my coils are distributed nicely around the object, then yeah, it's pretty much almost uniform. So my coil sensitivity is of, you know, let's say coil sensitivity of coil. The sensitivity of coil 1 is take image from coil 1 and then divide that image with a square root sum of squares. And so hopefully, you know, what you left up with is something that is not weighted by the image, it's just weighted by the coils, and that is actually the result of it. So this is one way of obtaining coil sensitivity maps, and you could also smooth them. Okay. Now, the thing is, you can only know where the coil, like what the value of the coils are when there is a signal. When there is a signal, you can't actually measure them. And so, for example, there's no signal like, you know, kind of on the edge here, right? So then it's going to be noisy. But, you know, smoothing, actually, you can estimate what is the sensitivity over there too. Okay, so in the case of the body coil image, the coil sensitivity is coil gamma divided by the image from the body. Now, what is the image in coil gamma? Well, it's the image from the body multiplied by the coil sensitivity of coil gamma. So if you divide by m, then you should be able to get the sensitivity of coil gamma. Does that make sense? Okay. In the case of SSOS, well, I'm assuming, so this is coil gamma, it's m times s gamma. And this is a square root sum of squares, right? But, so what I'm gonna get is really, I'm gonna get what's called normalized sensitivities, because then m cancels, and then I'm gonna get s gamma, but divided by the square root sum of squares of all of these. So it's pretty much normalized to 1. Kind of like the value is normalized. Does that make sense? Okay. Okay. Now let me quickly just say something. So there's another method that's really popular. It's called the Walsh method, implemented also in Siemens scanner. It's called adaptive kind of coil combination. And the idea there is the following, described by this paper. It's a really nice method. It's saying the following, you know, coil, the image from coil S is S times, like the weighted images, sorry, the weighted images is S times M. That's the weighted coil images. Okay. Now, yeah, if I go and combine them, so I can take S conjugate times MS divided by S conjugate S, then I will get M. You know, this is how I'm going to take these and I'm going to combine them using the coil combination, the regular coil combination that, you know, from the Romer paper that we described last time. This is pretty much what it is. This is the square sum of the coil sensitivities, S conjugate S, and the top of S conjugate times M. Remember? That's from last time. This is the regular. Okay, so this is multiplying the image with this will give me the combined image, a single image. Okay, but if I get a single image and I multiply it by S, right, that should also be true, right? That should, right, this thing should also be true, right? But that is also MS, right? So MS, the coil sensitivities, the individual coils, is really taking the individual coils, combine them, and then multiplying back by the maps. Right? That should give me exactly the coils. Does that make sense? Again, I take the individual coil images, I combine them into a single one, and then I multiply again by the coil sensitivities, and that will give me the individual coils. So then basically this is a null operator, like it does nothing. It's kind of like identity, right? Okay, so this is a good equation, right? But the thing is, this, let's say I have 8 coils, okay? Let's say I have 8 channels. Then, and so I'm gonna get like, MS would be 8 by 1 pixels, because I've got, you know, 8 coils, images. So for every position, I'm gonna get 8 pixels. This matrix here is gonna combine them into 1. So it's, this one is 1 by 8. Okay, this is MS. And this is S conjugate over S conjugate S. It's a 1 by 8. And then S is again 8 by 1. This is the coil sensitivities. Okay, so that is S. Okay, and that equals an 8 by 1. So MS. Okay, all right. So pretty much what it means is that there's a rank 1 matrix. A rank 1 matrix that, you know, this, like basically these coils live in this vector lives in a one-dimensional space, because I can combine it into one value and then expand it again, and I didn't lose any information. So although you have 8 values, it lives in a one-dimensional space. Does that make sense? Okay, so the idea there is effectively to estimate that subspace. And let's see if I can actually do it for you. Yeah, what I'm going to ask to say, you know what, the coil sensitivities are, well, I don't know, this is going to take time. So let me just kind of give you the idea. All right, basically I'm going to say the coil sensitivity don't change in a small window, right? Like if I look at a small window, the coil sensitivities don't change much. Okay, they don't change. So effectively, I'm going to have the same S for all of those positions. All these pixels will have the same value of S. Okay, S1, S2, S3, you know, all these will be the same for all those pixels. Okay, so now I kind of have like a few observations of the same S. And so what I'm going to do is I'm going to use it to estimate the subspace. So here's the idea: is I'm going to take this coil, a window from the image. This is one window, and then another window, another window. Each one comes from a different coil. And then what I'm going to do is I'm going to take this, and I'm going to effectively, put that in a row of a matrix. And I'm going to take this one, I'm going to put it in a row. I'm going to take all the pixels here, and I'm going to put them in a row of a matrix. And I'm going to take all the pixels here, and I'm going to put also in a row of a matrix. And I'm going to take all those pixels here, and I'm going to put in a row of a matrix, right? Then, because they have the same S associated with them for all those observations, for all these pixels, the dimensionality of this matrix, even though it's 8 by 21 squared, it should be much smaller. And if I can do an SVD, singular value decomposition of this matrix, I can see that it can be decomposed into U sigma V, and you can see that it really has a single dominant singular vector. So that means that this matrix can be described by U1 sigma 11 V1 transpose conjugate, which is pretty much, this is S conjugate over S conjugate S, and this is S. And so basically, effectively, I can estimate now the coil sensitivities that way using a singular value. And what I'm going to do for the entire image is do a sliding window. You know, like I'm going to move this window and then going to consider the coil sensitivity, the one like in the center. Okay, so just move it around. And this is the result that, you know, this estimation gives you. It's pretty good. Okay, so it gives you a really nice estimation of the coil sensitivities. And this is the Welsh method, and it's an adaptive method, because it basically, there's no assumption here. I didn't divide anything. What I did is really just took a window and then, stacked this into a matrix and computed an SVD. And because exploited the fact that my data is low rank, right? I'm observing one image through 8 channels. So I should really have, instead of 8 dimensionality, I should really have 1. And so that's the idea. Okay, if you're interested in the details, please read the paper. It's really nice, nicely explained. All right. I wanted to talk more about, oh yeah, the other last thing that people do is they try to do self-calibration. So they collect an image that is accelerated, but in the low resolution of K-space, they collect full K-space. And then they'll go and use this. This doesn't have aliasing, but it's low resolution. But because the coils are smooth, then using low resolution may be enough to estimate the coil. So what you do is you use this part of K-space in order to compute low resolution images, and then you compute sensitivity maps out of that. Once you know the sensitivity maps, then you use sense in order to reconstruct the missing information. Okay, this is called MSense. And then I don't want to talk about grappa now, so I'm going to stop here. Okay. So anyway, thank you very much for taking the class. I really appreciate that. Hope you enjoyed it. And I'm looking forward to seeing you talk next week and me and Eking asking lots of questions. All right. Well, thanks so much and have a nice day. Bye, everyone.